Recently, dark matter was joined by dark energy as one of the most profound sources of ignorance the astrophysicist faces today. What we found is that there's a mysterious pressure operating in the vacuum of space, and it's combating the gravity and winning. We don't know its origin. We don't know what it is. We're not even sure of its long-term effect.
What if I tell you that a mysterious network of connections exists, linking everything in the universe? An invisible web of matter shapes the universe, concealing its origin and evolution. Recently, scientists discovered one of the earliest and longest strands of this cosmic web. It spans 3 million light-years, holding 10 ancient galaxies and an extensive black hole. Sounds amazing, right? Well, that's exactly what we're going to discuss in today's video. Join us as we explore this amazing discovery made by scientists using NASA's James Webb Space Telescope and what Neil deGrease Tyson has to say about this discovery. So without further ado, let's get started. To start off, let's delve into the concept of the cosmic web. The cosmic web refers to the vast structural arrangement of material in the universe. This intricate network comprises threads of dark matter and gas that interweave, giving rise to intersections housing densely clustered galaxies, while expansive voids separate them. Despite being imperceptible to our eyes, the cosmic web's predominant composition, dark matter, remains invisible, neither emitting nor reflecting light. This enigmatic substance, constituting around 85% of the universe's matter, reveals its existence through gravitational influences on ordinary matter like stars and galaxies. Coined in 1996 by Richard Bond of the University of Toronto, the term cosmic web drew inspiration from the pioneering work of Yakov Zuldovich and associates. They demonstrated that minute variations in early universe matter density could evolve into extensive gravitational patterns, shaping into sheets, threads, and nodes of matter. These patterns later gained validation through galaxy surveys and structural formation simulations. The cosmic web emerges from billions of years of gravitational attraction and cosmic expansion post the Big Bang. In the universe's infancy, marked by high temperature and density, slight material distribution fluctuations took hold. Over eons, gravity acted as a force, drawing more material into these fluctuations. These fluctuations laid the groundwork for the cosmic web, evolving into clusters and strands of dark matter that traverse space. As the universe expanded, these structures became more distinct and discernible as ordinary matter followed the path of dark matter, coalescing into stars and galaxies along these interconnected threads. Furthermore, the cosmic web is not still active and changing. Matter is always moving from the empty spaces into the threads and from the threads into the groups, where galaxies collide and come together. It also changes shape as the universe expands, stretching and distorting its threads. We study the cosmic web to better understand how galaxies form and change over time and how they are affected by their surroundings. But how can we study something that is unseen? One of the best ways to do that is to use powerful telescopes that can observe faraway galaxies and quasars. Quasars are extremely bright objects that are powered by very large black holes at the centers of galaxies. They are so bright that they can be seen across billions of light years, making them ideal tools for exploring the early universe. Quasars also have a strong effect on their surroundings as they emit intense radiation and jets of particles that can heat and change the gas around them. Recently, scientists using NASA's James Webb Space Telescope have made an astonishing discovery. They have found a thread-like arrangement of 10 galaxies that existed just 830 million years after the Big Bang, connected by a thread of dark matter and gas. This thread is anchored by a very faraway and bright quasar called G0305, which appears in the middle of a group of 3 galaxies on one end of the structure. The quasar's brightness is greater than its host galaxy, making it difficult to see with other telescopes. This is one of the earliest thread-like structures that people have ever found associated with a faraway quasar. It spans 3 million light-years across, which is about 30 times larger than our own Milky Way galaxy. The thread contains enough matter to make hundreds of billions of stars, and it is likely to grow even larger over time as more matter flows into it. Scientists believe that this thread will eventually change into a large group of galaxies, much like the well-known Coma group in the nearby universe. The ASPIRE project, which made this discovery, has as its main goal to study the surroundings of the earliest black holes. The project uses the Webb near-infrared camera to observe 25 quasars that existed within the first billion years after the Big Bang, a time known as the epoch of ionization. This was when the first stars and galaxies ionized most of the hydrogen gas in space, making it clear to light. But why is this discovery so important? Well, it tells us a lot about how the cosmic web formed and changed in the early universe, and how it affected the formation of stars and galaxies. For example, we now know that threads were already present and visible at such an early time, and that they were associated with quasars and galaxies. We can also see that quasars can create bubbles of changed gas around them, which can affect the temperature and density of the surrounding matter. And it shows us that the cosmic web is not the same everywhere, but has differences in structure and properties. But how did very large black holes exist and grow in the early universe? And how did these early, very large black holes potentially control the formation of stars in their galaxies? These are some of the questions that the ASPIRE project aims to answer. Very large black holes are thought to form from smaller black holes that come together or gather large amounts of gas from their surroundings. However, it is not clear how they could grow so fast and so early in the history of the universe when the available gas and time were limited. One possibility is that they formed from the direct collapse of large clouds of gas, skipping the middle steps of star formation. Another possibility is that they were started by the leftovers of the first stars, which were much larger and short-lived than stars today. Moreover, very large black holes can also affect the formation of stars in their host galaxies by either slowing or enhancing it. On the one hand, they can slow star formation by heating and blowing away the gas that would otherwise form stars, or by stopping more gas from falling into the galaxy. On the other hand, they can speed up star formation by triggering changes in turbulence in the gas, or by causing gravitational instability that leads to star formation. The balance between these effects depends on many things, such as the mass and spin of the black hole, the properties of the gas, and the feedback mechanisms involved. ASPIRE, through the study of quasars, associated galaxies, and cosmic threads, offers a comprehensive understanding of the intricate processes governing the universe's evolution. By scrutinizing these celestial phenomena, ASPIRE unveils the profound influence of massive black holes on the cosmic web's development and the emergence of cosmic structures. One remarkable aspect elucidated by ASPIRE is the assessment of gas availability for star formation within distinct segments of cosmic threads, unveiling the intricate interplay with the quasar's radiation. The mission's capabilities extend to contrasting galaxy properties in close proximity to quasars versus those situated farther away. This juxtaposition allows ASPIRE to discern disparities in star formation rates and historical trajectories, shedding light on the intricate relationship between cosmic environments and galactic evolution. ASPIRE's significance is further underscored by its role in verifying diverse models pertaining to the genesis and expansion of black holes. By meticulously comparing these models against empirical evidence, ASPIRE determines the most congruent explanations for observed phenomena. Through meticulous observation and rigorous analysis, ASPIRE's insights foster a more profound comprehension of the universe's mechanisms, unraveling the enigmatic forces shaping its grand tapestry. One of ASPIRE's most significant contributions lies in its role as a testing ground for theoretical models. The mission actively evaluates diverse hypotheses concerning the formation and expansion of black holes, assessing how well they align with observed phenomena. This process allows scientists to refine and validate their theories, inching closer to a unified understanding of the universe's most enigmatic processes. In essence, Aspire's holistic approach to studying quasars, galaxies, and cosmic threads enriches our cosmic narrative. By unraveling the complex interplay of forces at play, Aspire fosters a deeper appreciation for the intricate dance of creation and transformation that has been unfolding since the universe's inception. Thank you for watching this video. We hope you enjoyed learning about this amazing discovery and how it helps us understand our universe better.